due a week from today. In the online lecture notes, there's a reference to the homework assignment. It's wrong. For the authoritative version of what the assignment is, you have to look at the website under homework. In addition to some problems from Chapter 2 of the book, I've also added some additional problems. So last time, how come you're not outside on a day like this, you know? I'll tell you why. It's because Caltech not only has the greatest weather, we also have great physics classes. So it's my job to make you not regret that you got out of bed and didn't go to the beach. Those things would have been nice too. But today, you get introduced to two of the heroes of thermal physics, characters who will have leading roles throughout the term, entropy and temperature. Okay? Very important concepts. We talked about the fundamental assumption of statistical physics. And there are a couple of points I want to amplify, which I didn't emphasize so much before, by stating the assumption this way, with two qualifiers. One is accessible, which apparently I don't know how to spell, accessible states, and another qualifier of a closed system are equally likely. So a closed system means a closed system. The system doesn't interact in any way with its environment. If we have conservation of energy and particle number, we can imagine specifying the total energy U and the total particle number N. And once they're specified, they'll stay constant if particle number and energy are conserved, and the system can't exchange particles or energy with any other system. That's what I mean by closed. Although we won't necessarily be able to specify the energy and the particle number with perfect precision, but instead we'll say that the energy is in some narrow range with a width delta U, and similarly for the particle number, this uncertainty in particle number and energy we'll always consider to be small, but not necessarily zero. So the precision by which we specify the energy is small compared to the total energy, and similarly for the particle number. That's what I mean by closed. What do I mean by accessible? Well, here there's a little bit of a subtlety, which is a question of time scales. So I'll say can occur on relevant time scale. So, for example, we might be doing experiments with a hunk of graphite, a carbon lattice, and there's another form for the lattice of carbon which is possible, which is diamond. And it's actually more stable. Well, which is more stable depends on the pressure and stuff like that. But if we have a hunk of graphite, it's possible, because of some fluctuation, for it eventually to spontaneously become diamond. But the time scale for that is incredibly long. So we really don't have to worry about it. We can consider the states that are accessible to be states of graphite, not worry about the states of diamond. Or if you have a gas in a box, there are lots of different microscopic states depending on how the molecules divide up the total energy, their positions and momenta. It's possible for that gas to spontaneously fluctuate to a configuration in which almost all the energy is in a little black hole in the corner of the box. And there are some settings in which you might want to consider such fluctuations, but if you're interested in the behavior of a gas under normal laboratory conditions, you don't have to worry about the black hole as being one of the accessible states. Potentially the system can fluctuate there, but it'll take so long before such a fluctuation is likely that we don't worry about it. That's what I mean by accessible. I actually mean two things by accessible. I mean that possible states on the presumed time scale, and also consistent with the way we've specified the macroscopic quantities to a particular precision, with energy and particle number and the appropriate range. And then with U and N specified to that accuracy, we can speak of the multiplicity, we'll usually denote it by G, and that's the number of accessible states which is consistent with specified range of macroscopic quantities like energy and particle number. And our assumption is that of all these many states, typically there will be many in a large system, they're all equally likely. We're completely indifferent as to whether the system is in one of those states or another. So we can imagine a probability distribution on those possible accessible states which is completely uniform, in which each one of the states has the same probability. So for each state, it'll just be 1 over the multiplicity. So a uniform distribution on the accessible states. And the way we'll use the probability distribution is we'll compute expectation values of observables, things we want to compare to experiments. And the reason it works is that when the system is very large, the fluctuations around mean values are small. That's what we talked about last time when we considered, for example, flipping a coin many times. So we'll evaluate expectation values in this ensemble of states. So I'll sum over states, consider the value of this observable in a particular state, weighted by the probability of that state. And like I said, we'll usually consider the uniform distribution over accessible states when we compute such ensemble averages. And the main lesson from last time was if we consider a big system, it means fluctuations about the mean values are small. So by calculating these expectation values in the ensemble, we can predict pretty well the behavior we'll see when we observe the system. Big fluctuations are rare. Okay. So that's kind of where we were last time. Any questions about that stuff? Okay. All right. So what I next want to talk about, to sneak up on the important concepts of entropy and temperature, is thermal contact between two systems. So just to have something concrete to think about, we can think of our system as being a gas in a box. And at least to some precision, we specified the number of particles and the energy in the gas. Well, suppose we have two such systems. And initially, they're completely isolated from one another. So two boxes. And so there's a definite, up to some small accuracy, some small error, a definite number of particles and energy in both box 1 and box 2. Now I bring them into contact, into a particular type of contact, what I call thermal contact. And what that means is the number of particles in box 1 was initially N1, in box 2 was N2. Thermal contact means particles can't pass from one box to the other, so it's still N1 in box 1 and N2 in box 2. But energy can flow between the boxes. So energy can be exchanged between system 1 and 2. But particle number cannot be. And so we want to know, when we bring the boxes into contact, what's going to happen to the energy. Okay? After a while, the energy in box 1 is no longer going to be U1. In box 2, no longer U2. What's going to happen? Well, the total energy is conserved. Energy flows to box 2 from box 1. The amount by which the energy in box 2 increases is the amount by which the energy in box 1 decreases. So U equals U1 plus U2 equals constant. Because the two boxes together, as a joint system, is a closed system, and there's no way for it to gain or lose energy. Now, before we establish the contact, what can we say about the degeneracy? Well, there's some number of accessible states for box 1. So I'll call that G1, which is a function of N1 and U1. There's some degeneracy or multiplicity for box 2. The total number of accessible states for the pair of boxes is just the product. Okay? All possible states for box 1, all possible states for box 2, when the number of particles and the energy in each box is specified. Okay? But now, they're brought into contact. So when we speak of the accessible states, we have to consider all the possible ways in which the total energy U could be shared between the two boxes, right? So now, the multiplicity for total particle number n, which is just the sum of n1 and n2, of course, both n1 and n2 are going to be fixed because there's no exchange of particles. Now, to describe all the accessible states, I want to consider all the ways the energy could be shared between the two boxes. So, for box 1, in the worst case, it has none of the energy. In the best case, it has all the energy. So U1 varies between 0 and U. And when box 1 has energy U1, then box 2 has energy U minus U1. So I consider the multiplicity of box 2 for energy U minus U1. Okay? Now all the states are accessible, so in determining the multiplicity, I should count them all. And this is where the key idea of statistical mechanics comes in. So I claim if I consider the multiplicity, by the multiplicity I mean for some fixed U1, the product of the multiplicities of the two boxes, so I'll call that G1, G2, as a function of U1, when for a large system size, G1, G2 is sharply peaked, as a function of U1. Looks something like that. And there's some value where the product of multiplicities is maximized, where the center of the peak is, which I'll call U1 hat. That's the way of sharing the energy between the two boxes that makes the total number of states as large as possible. So I'll call U1 hat when box 1 has energy U1 hat and box 2 has energy U minus U1 hat, the most probable configuration. So the word configuration here doesn't refer to one particular state, but rather one particular way of sharing the total energy between the two boxes. When box 1 has energy U1 hat and box 2 has the rest of the energy, that's when the total number of accessible states is the largest possible. It's a big number. So by configuration, I just mean the way of dividing up the macroscopic resource that the two boxes are sharing, the way of dividing it up between the two boxes, which gives the most states, which according to our fundamental assumption will be the most probable way of sharing the energy. So that's why it's called the most probable configuration. It's also sometimes called, also known as equilibrium configuration. Okay? So where does the peak occur? What's the value U1 equals U1 hat that the system likes? Well, you just have to maximize a function, the product of G1 and G2, as a function of U1. So I can ask, where is the product G1, G2 stationary? That's where the maximum will be. So dG equals dG1, G2. What's the first order variation of the product G1, G2? Well, if I just differentiate by the product rule, I can say, consider the partial derivative of G1 with respect to the energy in box 1, U1, and I'm keeping the particle number held fixed, so I'm just reminding you I'm taking a partial derivative. The multiplicity is a function, in principle, of the energy and the particle number, but we're only allowing the energy to vary here, not the particle number. So I'm considering the derivative of the multiplicity with respect to energy, but with the particle number held fixed. So the first order change, if there's a small change in the energy U1 of G1, is given by this partial derivative times du1. And then by the product rule, I have that times G2 plus G1 times the derivative of G2 with respect to the energy in box 2, with the particle number in box 2 fixed, times du2. Okay? And at the peak, that's equal to 0. The first order variation of the multiplicity is 0, right at the top of the peak. And since the energy is conserved, the total energy U equals U1 plus U2 is fixed. That means that du is equal to 0, or du2 is equal to minus du1. So if the energy in box 1 increases a little bit, the energy in box 2 decreases by the same amount because the total energy is fixed. So I can write dg as partial derivative of g1 with respect to u1 with n1 fixed times g2 minus g1 partial derivative of g2 with respect to u2 with particle number in box 2 fixed, multiplying du1. The same thing I wrote down before, but with du2 replaced by minus du1. And that's what's supposed to be 0 at the peak. So the condition for the most probable configuration is partial derivative of g1 with respect to u1 with n1 fixed times g2 is equal to partial derivative of g2 with respect to u2 with n2 fixed times g1. And if we divide by g1, g2, well, if you don't mind me doing this, g2 then becomes 1 over g1. And this becomes 1 over g2. So in other words, these are derivatives of natural logarithms of g1 and g2, which we've equated. So our condition for the most probable configuration is partial derivative with respect to u1 of natural log of g1 with n1 fixed is equal to partial derivative with respect to u2 of log of g2 with n2 fixed. So then we can solve that to determine u1 hat, the most probable configuration. So since it arose in a natural way in this setting, this log of the multiplicity is an important quantity which motivates this definition of entropy. The entropy of a system, which I'm going to denote by the Greek letter sigma, is a function of the particle number and the energy, and it's just the log of the multiplicity, the number of accessible states. Okay. So the nice thing about entropy is that it's an additive quantity. If I have two systems which are isolated from one another, as in the original premise of our discussion, for two isolated systems, the multiplicity is G1, G2, and the total number of accessible states is the product of the number in system 1 and the number in system 2. So correspondingly, the entropy will be additive, since the log of a product is the sum of the logs. So entropy has the property that it's what we call extensive. If you have a system with many parts, that means it's proportional to system size. Okay. So our condition for the most probable configuration, using our definition, can be restated in an equivalent form. It's the way of sharing the energy such that the partial derivative of entropy of system 1 with respect to U1 with N1 fixed is equal to partial derivative of entropy of system 2 with respect to its energy with its particle number fixed. And that we can solve to determine U1 hat, the amount of energy in system 1 in the most probable configuration. Now, when we're not in the most probable configuration to begin with, the systems were isolated from one another. So in general, when we bring them together, they won't be in the most probable configuration. So what's going to happen? Well, they're going to seek out the most probable configuration. That's our fundamental assumption, that a system, never mind the microscopic details of exactly how it manages to do this, let's just assume it's true, that the system comes to equilibrium. It seeks out its most probable configuration where the multiplicity is as high as possible. So if we look at the total entropy of the systems combined, which is just the log of G1, G2, like I was discussing before, well, the product is sharply peaked, so is its log, though not quite as sharp. So as a function of U1, the logarithm has a peak at U1 hat. So suppose when we bring the systems together, U1 is actually below U1 hat. Well, then it's going to want to climb the hill. The energy in system 1 will want to increase in order to seek out a more probable configuration. And if it starts out with too much energy, then U1 is going to want to lose energy to seek out the most probable configuration. So in other words, if the total entropy, sigma 1 plus sigma 2, has a derivative with respect to U1, which is positive, that means it can find a more probable configuration by gaining energy, and that means when the systems are brought into contact, U1 will want to increase. blackboard. And remember, the derivative of sigma 2 with respect to sigma 1, of sigma 2 with respect to u1 is minus its derivative with respect to u2, since the total energy is conserved. So this condition I can rewrite as d sigma 1 du1 with n1 fixed minus d sigma 2 with respect to u2 with n2 fixed greater than 0, then the consequence will be energy flows from 2 to 1. So now to get to a more probable configuration, u1 wants to increase. How does it do that? Well, it borrows more of the energy from u2, so it has a bigger share of the total energy. On the other hand, if the derivative with respect to u1 of sigma 1 plus sigma 2 were negative, that would mean we're over here, and to get to the more probable configuration, we would want u1 to decrease. And that means energy flows from 1 to 2. System 1 wants to give up some of its energy to system 2 so that the overall configuration will be more probable. And so again, I can write this as derivative of sigma 1 with respect to u1 with n1 fixed minus derivative of sigma 2 with respect to u2 with n2 fixed less than 0 makes energy want to flow from 1 to 2. And that motivates another definition. Does this remind you of something? You got two bodies. You bring them into thermal contact. Energy can be exchanged between them. The energy wants to flow in a preferred direction from either 1 to 2 or 2 to 1, depending on which one of these inequalities is satisfied. What does that sound like? It sounds like temperature. It sounds like heat flow. Heat flow, tell me if I've got this right, goes from a system that's hot to a system that's cold. Okay? You bring them into contact, and that's what's going to happen. The energy flows in a preferred direction, determined by which system is hotter. Therefore, I suggest that we define temperature. And since I've already committed myself to denoting entropy by a Greek letter sigma, I'll denote temperature by a Greek letter tau. And I'll define 1 over tau as the derivative of entropy with respect to energy with particle number fixed. So our expression for the first order change of the total entropy when a little bit of heat flows between the two systems, using the definition of temperature, becomes 1 over tau 1 minus 1 over tau 2 times du1. That's what happens under thermal contact when the total energy u1 plus u2 is fixed. Now, just to make it a little bit confusing, I define temperature as the reciprocal this partial derivative. But I've done it in such a way as to be consistent with our intuitive notion that energy likes to flow from a high temperature system to a low temperature system. In fact, first of all, what can we say about the most probable configuration, or equilibrium? In equilibrium, we're at the peak. Okay? So the first order change in the total entropy is 0. And that'll be true if the two systems have the same temperature. So equilibrium, meaning we're at the most probable configuration and it's not favorable for energy to flow in either direction, means the two systems have the same temperature. If system 2 has higher temperature and we want d sigma to be positive because we want to go to a more probable configuration, so if tau 2 is larger, then this is positive multiplying du1. That means we want du1 to be positive. Or in other words, heat or energy flows from 2, the hotter body, to 1. And if tau 1 has the higher temperature, and again we want d sigma to be greater than 0, now the coefficient of du1 will be negative. To get to a more probable configuration, we'll want du1 to be negative. That means heat is flowing from 1 to 2. Okay? So, same temperature, there's no heat flow, we're in equilibrium. Otherwise, in order to seek out the more probable configuration, energy flows from higher temperature to lower temperature. Now, the way I've defined it, entropy has what units? Is it in, meters, kilograms? Sigma, what are the units of sigma? It's dimensionless. Has no units. It's just the log of a pure number we got from counting states. Temperature, which is defined as 1 over temperature, equals derivative of entropy with respect to energy, therefore has the units of what? All right, tau has units of energy. So we can measure it in joules or ergs or something. But we usually don't speak of temperature that way. Instead, we speak of degrees Kelvin. But my definition of temperature is the same thing as Kelvin's temperature scale, except for a conversion constant. I've used the symbol tau for temperature because, as you know, by the time you've gotten to Physics 12C, physicists love Greek letters. Usually we write temperature as a Latin capital T. So my temperature tau, which has the dimensions of energy, we can write as a conversion factor called K sub B times conventional temperature. This is known as Boltzmann's constant. So, for example, if I want to measure temperature in degrees K and energy in ergs, then Boltzmann's constant is about 1.4 times 10 to the minus 16 ergs for each degree K. There's also a more conventional way of defining entropy. Let's see if I can get this right. For conventional entropy, which I'll denote by capital S, we can write 1 over conventional temperature as the partial derivative of conventional entropy with respect to energy, with n fixed. So I guess that means that S is equal to Boltzmann's constant times sigma, unless it's the other way around. Okay. All right. So we talked about the most probable configuration, well, just like we talked about last time when we were looking at the states of a magnet. Now let's talk about the fluctuations for a minute, because remember, the key idea is that when we have a large system, big fluctuations are very rare. And let's talk about this in a particular example. In fact, so we can use our work from last time. I won't consider gas in a box. We'll do gas in a box later. But I'll consider a magnet. Like the model of a magnet we used last time, where there are a bunch of spins, and they're each either up or down along the z-axis. And then we saw that the multiplicity, if I considered the number of upspins to be half of all the spins plus some deviation s, we could write the multiplicity of the number of states as a function of s. It has its peak at s equals 0, where it takes the value g of n 0, and then it falls off like a Gaussian as s increases. Specifically, we saw it falls off like e to the minus 2 s squared over n. Okay, from the lecture on Tuesday. Now this doesn't yet have anything to do with energy, and now I'm talking about energy and the number of states as a function of energy. So let's make it have something to do with energy by imagining turning on a magnetic field. Well, the spins have magnetic moments, and so when I turn on a magnetic field, those little magnetic moments want to line up with the magnetic field. So the energy for a spin in a magnetic field, since this has magnetic moment m, is minus m dot b. Well, in my case, I'm just considering the spins to be either up or down. So they're either aligned with the field, which is the energetically preferred case, which has the lower energy, minus mb, or they're anti-aligned with the field. And the spin that's anti-aligned has energy plus mb. So the two states, aligned and anti-aligned, this one has energy minus mb, and this one has energy mb. Okay? If I want to know the total energy, I just sum up the energies of all the spins. So U is plus mb for each downspin and minus mb for each upspin. So I can write it as a minus the number up minus the number down times mb. And the number up minus the number down, since the total number is n, the number down is 1/2 n minus s. The difference between the number up and the number down, which I'd call the spin excess, is 2s. So now we have energy equals minus 2s mb, and we can think of our multiplicity that we computed last time as a number of states that depends on the energy. Okay? Because I've made the energy essentially equivalent to the excess of spin up over spin down, up to a factor. So now I want to imagine two magnets. They're both in the magnetic field. And because the energy is conserved, when the magnets are isolated from one another, the spin excess of magnet 1 is fixed, right? Because it doesn't have any way of gaining energy or losing energy. And its energy is just proportional to the spin excess. Excess. Okay? So I have magnet 1, magnet 2. Each has a specified spin excess, which is fixed. But then I bring them into contact. Now they can exchange energy. Now the spin excess of magnet 1 can change at the expense of the spin excess of magnet 2. The total energy is preserved, but the energy of each can change. So initially, the magnets have a number of upspins, half the spins plus S1, half the spins plus S2, respectively. Then we bring them into contact. Everybody's in the same magnetic field. So the total spin excess is preserved. So S equals S1 plus S2 is fixed. But S can be exchanged between the two magnets, and the system will now find the optimal way, the most probable way, of sharing the spin excess between the two systems. So when the spin excess is S1 in system 1 and S2 in system 2, then the number of states is just the product of this degeneracy or multiplicity factor for each one of the two magnets. So G1, G2 is equal to G1, the number of spins N1, G2, the number of spins N2, and S equals 0, times these Gaussian factors, e to the minus 2 S1 squared over N1 for system 1, and e to the minus 2 S2 squared over N2 for system 2. And the entropy, the total entropy, is just the log of that expression and there's a constant term, which actually isn't going to be very important in our discussion, which is the log of this prefactor, which doesn't depend on S. And then the log of this part, which will be minus 2 S1 squared over N1 minus 2 S2 squared over N2. So the system wants to find a way to maximize this quantity, which is just an upside-down parabola, by finding the best way of sharing the fixed total S between the two systems. So since S is equal to S1 plus S2, sigma is equal to that S independent constant minus 2 S1 squared over N, 1, and minus 2 S minus S1 squared over N2. So now all we got to do is find the maximum of a quadratic function in order to find the most probable configuration. So d sigma, ds1, from differentiating the first term, I get minus 4 s1 over n1. And from differentiating the second, I get plus 4 s minus s1 over n2. And that equation determines its solution is S1 hat, the most probable configuration. So I can put this over on the other side. I can divide out the 4s. So the most probable value for S1, S1 hat divided by N1, is equal to S minus S1 hat over N2, or in other words, the most probable value of S2 divided by N2. Well, of course, coming back over here, I can just solve for S1. I can write S1 hat times 1 over N1 plus 1 over N2. If I put this minus S1 over N2 over on the other side, well, will be equal to S over N2. From this S over N2, I divided out the 4s. And this is just N1 plus N2 over the product, N1, N2. The N2s in the denominator divide out from both sides. So we've determined the most probable configuration to be S1 hat over N1 equals divide by the N1 plus N2, and the N2s divide out. And so it's S over the total number of spins N1 plus N2. So that's the equilibrium configuration that the system will seek out. But I said what we were really interested in is studying the fluctuations. How big are the fluctuations? Well, I should look at the this probability distribution. This must be over here. This number of accessible states, look at how it behaves as S deviates away, as S1 deviates away from its most probable value, S1 half. And for that purpose, I would like to expand the argument of the exponential here in a power series around the equilibrium value S1 half. So in other words, I can write the entropy when S is the most probable value S1 hat plus a small fluctuation, which I'll call delta, as an expansion in delta. The first term is sigma at S1 hat, the entropy in the most probable configuration. And then there's the derivative of the entropy with respect to S evaluated at S1 hat times delta, the linear term. The quadratic term is 1/2 second derivative of the entropy with respect to S evaluated at the most probable configuration times delta squared plus higher order in delta. So regarded as a function of delta, of course, this is just a constant. And this is 0 because we're at the most probable configuration, the peak of the entropy when S is equal to S1 half. The first derivative of S equals S1 hat vanishes. So if I look at the multiplicity, G1, G2, as S deviates from S1 hat by delta, that's e to the entropy. And using our power series expansion, that's some constant, which is just the exponential of that first constant term, times the exponential of the quadratic term plus higher order terms. So what's the second derivative? Well, here's the first derivative. If we differentiate again, the second derivative of the entropy with respect to S1 is minus 4, 1 over N1 plus 1 over N2. Or minus 4 times the total number of spins divided by the product N1, N2. So I have 1/2 of that second derivative times delta squared. So minus 2, total number of spins divided by n1, n2, times delta squared, plus higher order terms in delta. Okay. So now, what are the typical fluctuations like? Well, when the argument of the exponential, apart from the minus sign, is large compared to 1, then the multiplicity is very strongly suppressed. So under our hypothesis that all the accessible states are equally likely, those will be extremely unlikely configurations because there are very few states with that value of S1. Well, remembering that we want to apply this to macroscopic systems with a number of particles or a number of spins in this case, comparable to Avogadro's number, let's put in some appropriate numbers. Suppose the two magnets have comparable size, so the number of spins in magnet 1 is equal to the number of spins in magnet 2, or 1/2 the total number of spins. And that's, say, 10 to the 22 or so. And we can ask, how probable is a little fluctuation where delta deviates from the most probable configuration by an amount which is, say, 10 to the minus 10 of n1, the total number of spins in magnet 1. So the probability is proportional to, under our fundamental assumption, to the number of accessible states. So up to some prefactor, which we really won't try to estimate carefully, the probability of that fluctuation with delta over n1 of about 10 to the minus 2, I can write as the exponential of minus 4 n1. I'm using that n is equal to 2n1, so the minus 2 became a 4. Delta 1 over n1 squared. So this, we said, we want to consider to be 10 to the 22. And this now will be about 10 to the minus 20 because it's the square of 10 to the minus 10. And so this is going to be something like e to the minus 400, which would be something like 10 to the minus 174. So we have to emphasize, yeah, maybe they're prefactors. Maybe our estimate is just sort of a order of magnitude estimate. But 10 to the minus 174 is a ridiculously small number. I mean, does anybody know how old the universe is? 10 to the 18 seconds. Yeah, that's pretty good. 13.7 gigayears. And so maybe that's 5 times 10 to the 17 seconds, something like that. So if we have age of the universe (10 to the 18 seconds), and so what's the system is going to be, say, fluctuating, changing its configuration every once in a while. What's sort of the shortest time over which it could possibly change its configuration? Well, I don't know. But about the shortest time we know how to talk about that makes sense is the Planck time. It's the time that you can write down in terms of fundamental constants, like Newton's constant and h bar and c. And its interpretation is it's sort of the time scale over which, if you built a clock, the gravitational quantum fluctuations of the clock would be so big that the clock wouldn't be able to keep time. So it's sort of the shortest time we can imagine. And that's gh bar over c to the fifth to the 1/2. Okay? Gravity is weak. Newton's constant is really small. H bar, everybody knows that's small. C is really big. This is a time which is trying to be really small. It's about 10 to the minus 43 seconds. So let's say over the age of the universe, every Planck time the system was trying out a new configuration, it would have managed to, check out 10 to the 60, 10 to the 61 configurations or so. It's got a long way to go before it's ever going to find something which has a probability like 10 to the minus 174. So a fluctuation like this, with delta fluctuating compared to the macroscopic quantity by 1 part in 10 to the 10, when you have 10 to the 22 particles, that's my definition of never. It just can't happen. So this is really great because we've understood a lot today. When we have a system with many degrees of freedom, lots of molecules in a gas, lots of spins in a magnet, whatever it is, we can understand the concept of irreversibility. Or the arrow of time. There are certain things that want to go in one direction and essentially never go in the other direction. So, the case we've discussed today is if you have a hot body and a cold body and you allow them to come into thermal contact, there will always be heat flow from the hot body to the cold body until equilibrium is attained and you have two warm bodies. And in principle, that process is reversible. You could put two warm bodies into contact, and maybe if you waited a really long time, you'd come back and observe that one of them had become hot and the other had become cold. It's consistent with conservation of energy. But it never happens, because the number of configurations for the system when one of the bodies is hot and the other is cold is far, 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 far fewer than when both bodies are warm. So we can state the principles behind today's lecture very succinctly. And they're called the laws of thermodynamics. Well, the first law is just good old conservation of energy. So it says, in the context we've been discussing, 1 and 2 in thermal contact means that du1 plus du2 is equal to 0. What one system gains in energy, the other loses. And the second is the law of increase of entropy, or non-decrease of entropy. It says when 1 and 2 are brought into thermal contact, then the total entropy will change. A more likely configuration will be found. The sum of the entropy of system 1 and system 2 will not decrease. And if the system is not in equilibrium to begin with, it will increase. A more likely configuration will be found. Sometimes one speaks of the zeroth law of thermodynamics, which says thermal equilibrium is transitive So in other words, if 1 is in equilibrium with 2, meaning that when you bring 1 and 2 together, nothing happens and there's no flow of heat in either direction, and 2 is in equilibrium with 3, then 1 will be in equilibrium with 3. Well, we've understood where that comes from, because what determines whether there's heat flow, whether heat flows in one direction or the other, is the temperature. Being in thermal equilibrium means same temperature. So if 1 and 2 have the same temperature and 2 and 3 have the same temperature, so do 1 and 3. And just for completeness, I'll state the third one, since it usually comes along for the ride. The third law of thermodynamics, which we'll be discussing more later, says that if we consider the entropy, that it will go to a constant as the temperature tau goes to 0. So really what it says, and it's a consequence of quantum physics, that going to 0 temperature really means, as we'll see, that the system is in its lowest energy state. The entropy is just the logarithm of the number of states, so it means that the lowest energy state has some finite multiplicity. There aren't an infinite number of ground states. Okay, so this is all for closed systems. And I'd like to start talking about open systems, because most systems in practice really are open. So what I mean by an open system is, like most systems, there's some environment, and the system is in contact with its environment. It can exchange energy, perhaps particles, with its environment, like you in this room. And what we're going to do is we'll understand open systems by applying what we've already learned about closed systems. When I think of an open system, there's some system. I'll give it a name, system S. And it's in contact with some much larger system. That's the environment, which I'll denote by R. We usually call the environment the reservoir. And we call the system the system. We call the reservoir because that's what we call it. I guess a reservoir just means, in this setting, a big thing, and you can put a little bit of stuff in the thing, or you can take a little bit of stuff out of the thing. That's the reservoir. And what we'll imagine is the reservoir is everything else besides the system. It's the rest of the universe. So the whole thing is a closed system. Okay? So S plus R equals closed system, which isn't in contact with anything else, because the reservoir R includes everything of interest, which isn't an S. Now, up until now, in talking about the foundations of statistical mechanics, we've imagined that the system S is very large. I'm not going to do that anymore for the moment. The system S can be small now. S need not be large. It could be a single atom or something like that. But the reservoir is large. It's very large, being the rest of the universe and all. So we can use our fundamental assumption applied to the reservoir. Okay? Now the important point when I say that the overall system is closed is this. The system can fluctuate. Its state can change. When it does so, it exchanges energy with the reservoir. If the energy of the system goes up, where does the energy come from? It comes from the reservoir. If the energy system goes down, where does the energy go? It goes to the reservoir. Okay? So let's suppose that we think of the system as being in one of two possible states with different energies, E1, E2. And this is the system. And I really mean microscopic states. These aren't states with multiplicities like we talked about before. These have multiplicity 1. They're completely specified microscopic states. And we'd like to understand, when the system is in contact with the reservoir, what state the system wants to be in. Okay? Well, if it's in the state E1, if it wants to be in the state E2, it needs some energy, the difference between E2 and E1. It's going to get that from the reservoir, right? Well, what happens when it takes a little energy from the reservoir? The number of accessible states of the reservoir changes. Okay? So in order to understand how likely the system is to be in a state, we'll ask, what's the multiplicity of the reservoir? How is that affected when the state of the system changes? Okay, makes sense? So, according to our fundamental assumption, the probability of being in the state of the system with energy E1 divided by its probability. I'm going to take a ratio probability so I don't have to worry about the overall normalization. The ratio of the probability of being in the state with energy E1 of the system and the probability of being in the state with energy E2 of the system, that will be the multiplicity of the reservoir when it has total energy E0 minus E1. The whole energy of the world, system plus reservoir, call that U0. So if the system has energy E1, the reservoir has the rest, which is U0 minus E1. And the number of states of the reservoir, if the system has energy E2, is U0 minus E2. Okay? So, of course, I can write that as an exponential of its logarithm, something we love to do in statistical mechanics. So I can write it as the exponential of the entropy of the reservoir when it has energy U0 minus E1 minus the entropy of the reservoir when it has energy U0 minus E2. Now, what else do physicists love to do? Expand in power series. So let's have some fun. Look at the quantity in the what should have been parentheses here, and expand it in a power series expansion. So in the first term, I'll write it as entropy of the reservoir when it has all the energy, U0, then minus E1 times the derivative of the entropy of the reservoir with respect to its energy, evaluated at U equals U0, and then plus 1/2 epsilon squared times second derivative of entropy of the reservoir at U equals U0, and all the higher order terms in the power series expansion. But then subtract away the second term, which is, again, the entropy of the reservoir when it's got everything, minus E2 times d sigma r du, evaluated at U equals U0, and then plus 1/2 E2 squared, d2 sigma reservoir, du squared U equals U0, and plus the higher order stuff. Okay? Okay, now we come to an important point. Yes?
Why don't you include the state of the system?
Well, the reason I don't is because I'm actually assuming that each one of these is a single microscopic state, so there's no multiplicity of the system. I'm comparing two different, completely specified microscopic states of the system, so the only thing that contributes to the multiplicity is the number of states that the reservoir has. Okay, good question. Okay, so now we come to an important point. Remember I said entropy is, I mean, they're all important, but sometimes you've got to highlight one or two. The entropy, remember we said, is extensive. In other words, it's going to be proportional to the size of a system. In this case, the size of the reservoir, which is really big. So it's proportional to volume of reservoir. And same thing with the energy of the reservoir. Now, when I differentiate the entropy with respect to the energy, the volume scales out, right? It's in the numerator and the denominator. The result is an intensive quantity, a quantity which doesn't depend on the system size. So 1 over tau equals d sigma du is intensive, independent of volume. What about the second derivative? When I take the second derivative of sigma with respect to energy, now I'm differentiating 1 over tau, an intensive quantity, with respect to energy, an extensive quantity. So how do you think that's going to behave when the volume gets big? Right? It's going to scale like 1 over the volume. So this goes like 1 over volume. And when I consider then the reservoir to be extremely large, as I am, this is completely negligible. And that means that when I do my power series expansion, for once, I can actually justify truncating it. Well, I mean, hopefully I always can justify it when I do it. And all the other higher terms beyond the linear term become negligible in the limit of a large reservoir. This cancels this. All we've got left are these terms. The derivative of the entropy of the reservoir with respect to its energy is what we call, what? What do we call that? 1 over the temperature of the reservoir. Okay? So we've reached this conclusion. The probability of being in the state with energy E1 divided by the probability of being in the state with energy E2, we can write as the exponential of minus the difference of energies, E1 minus E2, divided by tau, where tau equals temperature of reservoir. Or for any state of our system, the probability of being in some microscopic state, which has energy Es, is proportional to e to the minus the energy of the state divided by the reservoir's temperature tau. That's an important equation. I don't do this that often, but this one gets a double box with a frame and, ribbons. This is called the Boltzmann factor. There's that guy again, Boltzmann. One of those geniuses whom I'm afraid was underappreciated during his lifetime, so he killed himself. But we honor him today. And what does it say? It tells us all kinds of interesting stuff. It tells us that when the temperature of the reservoir is small, the system's going to want to be in a low energy state. In fact, if it can be in either one of two states, say E1 or E2, if the temperature is small compared to the difference of energies, the system is going to have a big, big preference for being in the lower energy state. When the temperature gets really low, it's going to want to, with high probability, be in as low an energy state as possible. That's what the Boltzmann factor tells us. And we will explore its implications further next week. Okay.